Hey. So after having gained an intuitive understanding of what a limit is, as well as how to estimate and calculate limits, we are today going to look at the precise definition of a limit. I have to warn you, this is very technical. It often takes a lot of time to understand, and oftentimes students only understand a portion of it, but that is okay for most of you. If you are considering being a mathematics major, this is something you're going to have to understand very well eventually, because you're going to be looking at things kind of under the microscope like this in more detail in future math classes. But if you're not going to be a math major, it's okay to have a surface level understanding. We are going to get into the definition eventually, but I want to show you a couple of graphs to motivate why we need to have a more precise definition than we've been working with so far. So let me show you a couple of graphs of functions where we might be looking at their limits. So here are two graphs of functions. I'm going to call these functions f of x and g of x. And I'm not going to give you the equations that these functions came from. We're just going to look at the graphs of these functions for now. I might give you the equations later, so you can play around with them in a graphing calculator if you want. But for now, we're just going to call these f of x and g of x. And for each of these, we want to know the limit as x approaches 0. Now, if you look at this first function, and you look at what's happening to the y values as x approaches 0 from the left and right, it looks like the limit is going to end up being 0, right? It looks like we're approaching 0 from below and above as we go from the left and the right respectively. So it looks like the limit here is 0. And similarly, if we look at g of x, this looks to be like one of those that has sine or cosine of 1 over x in it, because it's looking like it's oscillating more and more in there. But maybe we've got the squeeze theorem here, because it is in the middle. You can see it is kind of getting closer and closer to 0. It does look like that limit might be 0. It looks like it's being squeezed to 0. But I want to zoom in on both of these graphs and have a closer look. Let me give you both of these graphs now in zoomed in form. All right, so here we have a zoomed in version of f of x, and here we have a zoomed in version of g of x, zoomed in closer and closer to the origin. And if you look at the graph of f of x, there's something interesting that's going on here. While the function is getting closer and closer to 0, there is an actual gap here. It is never actually going to reach 0, in the sense that there's a certain width here that it will always stay outside of, if that makes sense. Like, it's true, it's getting closer and closer to 0, but it will not get arbitrarily close to 0, meaning there's a certain point at which it stops getting closer and closer to 0. And this means that the limit does not exist. When there is a gap like that, the limit doesn't exist, because the right-handed limit is approaching whatever this is, 0.01 maybe, and the left-handed limit is approaching negative 0.01, and there is a gap between the left and right-handed limits, so that means that the two-sided limit does not exist. Now, this function is actually equal to 0.01 times the absolute value of x over x plus x, right? It actually looked like this function was just y equals x, but there's something else there, and that's what's causing this gap. And then if we look at the function down here, this other function, which also looked like the limit was equal to 0, it looked like it was oscillating an infinite number of times, which it is, but it also looked like they were being squeezed together. Like, we could use the squeeze theorem here to squeeze these between two functions where those limits are both 0. But again, we have an issue, And that issue is that this doesn't actually get squeezed all the way down to 0. It looks like the function that's on the top of this, the function above, only goes down to about 0.01, and the function below goes up to negative 0.01, and this is still oscillating between those values. In fact, the equation for this function is x squared plus 0.01 times cosine of 1 over x squared. And this is another situation where that limit as x approaches 0 does not exist, but that's because the function is still oscillating in between a range that goes from negative 0.01 to positive 0.01. So this is another situation where if we don't zoom in and we're kind of lazily looking at things, it looks like the function gets closer and closer to 0. But in fact, as we look very close to 0, that function is still oscillating between negative 0.01 and positive 0.01. And so the vague definition that we've been using, which has been, as x approaches a, f of x approaches some number L, that's not really rigorous enough. That's not specific enough, because we need our definition, kind of like a lawyer drafting up a contract and making sure there aren't any loopholes. We need to make sure that we don't accidentally have a situation where the function looks like it's getting closer and closer to 0, but it never actually hits 0. There's a gap in between that it never crosses. And we also need to get rid of this loophole where, yes, the function is kind of squeezing together closer and closer, but there's a problem, and that problem is as we approach 0, it is still oscillating back and forth between negative 0.01 and positive 0.01. So we need a very precise definition of a limit, kind of like a lawyer might make a contract, where our definition makes sure that we don't have either of these loopholes, either of these problems, where there's a gap that the function never goes in between around our supposed limit, or there's a gap that our function keeps oscillating back and forth between. Both of these are no-nos for limits, and so we need a better definition of limits that makes sure we don't have these problems, that closes those loopholes. And that's what we're going to talk about in the next video. But I wanted to show you these examples first so that you understand the loopholes that we need to fill in, the situations that our definition has to make sure we avoid.